John, about going back to the earlier discussion about prediction and our general ignorance as to explaining why the constants take their values. The broad point that strikes a philosopher is you've got so little to stand on, haven't you, in predicting the values. Johnston Stoney had it easy. He had laws he trusted, Avogadro's and Faraday's. Would you like to comment on which are the most likely among the 19 or 25 that we find in our three-dimensional scenario to be explained by some deeper background theory?
Yes, we know in the past that progress has been made, or people judge progress to have been made when certain things happen with constants. So, for example, while you may not explain the value of a constant, if you're able to relate one constant to another, say in an electroweak unification, then this is regarded as being a significant piece of progress. If you discover a new constant, so you discover a new physical phenomenon, which requires a new constant to explain it. So, for example, the acceleration of the universe with Landau. These would both be regarded as significant advances. I don't know of any progress that's on the horizon in actually explaining something numerically rather than relating it to other things. So what Johnston Stoney was really doing was finding the most fundamental way of expressing the relation between Avogadro's number and Faraday's law. And his key insight was that there was a single element of charge, that there was a basic unit of charge. And so the total charge was NE, as it were. But I wouldn't like to sort of bet on where someone is going to come along and attempt to provide an explanation for the fine structure constant or the mass of the electron over the mass of the proton. Of course, the fine structure constant is something that we define at low energy. As we go to higher energies, quantum vacuum polarization effects come into play, and the effective strength of interaction, say between two electrons, two charged particles, is no longer just defined by the fine structure constant, but by some effective fine structure constant, which takes into account the shielding of the charges by vacuum polarization effects of the opposite charge. So we know there are variations, as it were, in the effective value, say, of the fine structure constant or other couplings, but that's not really what we're talking about here. We're talking about variations in the so-called bare coupling with time. If you believe that there really is a nice unification, as Maldi and others at CERN have advertised for a long time, and that it's enhanced by having supersymmetry, so that you get a triple crossover of this apparent evolution in temperature of the couplings, then you might think that there is sitting out there a rather strong limit on time variation of those constants, because if you superimposed it onto the evolution in temperature, you would kill the nice triple crossover. And you've got a huge range of time in which to do it, going back to the early universe at 10 to the minus 35 of a second. So it could be that unification is only possible for particular values of the bare couplings, and that this would then make a prediction. You could turn it around and say it predicts the low energy values.
In what you were saying about the fine structure constant gradually increasing with time linearly, and then the cosmological constant comes in to stop that, how general is that, and how much is it just specific to your model?
It seems pretty general for these types of scalar field models, where the scalar field is modeling the variation of a constant other than the gravitation constant. So long as the constant involved is not significant, as it were, in the Friedmann equation, then it's just a consequence of the expansion rate. Okay, so it's just the same sort of thing as density perturbations not being able to grow. So it's not specific to this theory. It doesn't happen in general in Brand-Sticky theory. So Brand-Sticky G is turned off by going to an open universe, but not by having a vacuum energy stress. So if you put P as minus rho in Brand-Sticky theory, you get an exact solution with a fast variation in time, G proportional to 1 over time squared. But if you were to convert that to an evolution in the scale factor, it becomes very slow, because the scale factor goes like t to the Brand-Sticky omega plus a half. So it's very, very slow in A, although superficially not in T. But it is, I think, a sort of generic feature of models where the constant that's varying is not having a significant effect in the Friedmann equation. So its kinetic energy terms negligible there, for example.
Okay.